Let's wait for a couple of minutes to see if 2 3 other people join. Any doubts in the previous week's discussion hour or the content that I discussed last week?
Yes, sir. I do have small confusion, sir. I will ask in the, whenever the context comes, sir. Like you're discussing the quiz questions, no, sir. I'll ask.
Yeah. Okay.
Context comes. I'll ask, sir.
Okay.
Yeah.
Okay. Okay. So let's get started. So in today's discussion hour, we will discuss the questions based on dynamics of manipulators, and then we will move on to discuss the theoretical concepts around trajectory generation and path planning. So let's get started. And in between, wherever you feel that there is some gap in the understanding of the theoretical concept or in the explanation of the question, then you can just raise a question. So the first question says the mass distribution of a rigid body relative to a reference frame is represented by the, and the correct answer is the inertia tensor. So the inertia tensor is a 3 cross 3 tensor that we define and is generally expressed as in this form. And these terms, some places you can see them as negative ixy, negative ixz, and some places they will skip the negative sign and include it in the expression for ixy or ixz. So both are correct. So the inertia tensor that we have is symmetric, right? So this is first property is it's a symmetric matrix. And the diagonal terms that are there, they are calculated in a separate manner than the off diagonal terms. So I will give example of both. Like the first diagonal term ixx is calculated as the, it's a volume integral. So volume integral of the square sum of the y and z coordinates of that small element dv. So imagine this as a body, some arbitrary shaped body, and this is the point, the reference frame, right? And let's say here is a small volume. Okay, so this dv volume, so the location of this volume in this coordinate frame is some x comma y comma z, and this is the y and z that is being used here. So it's basically integration over all such elements in the object. So a volume integral of this expression multiplied with the density, right? So this is density, this is volume. So this is what is this is mass terms, and this is the squared distance squared. So you can relate it to the usual expression that you see for inertia, which is kg meter square, the SI units, or gram centimeter square, right? So the very simple formulae of inertia that you have learned is, let's say, a rod about its axis perpendicular to it rotate. So you have learned that about this axis the inertia is 1 by 12 ml square, right? This is L. So basically what does this describe is how is the mass distributed around a certain axis, set of axis. So the point which you can conclude from this is that it is dependent on the choice of axis. So inertia matrix is not a frame independent quantity, it is a frame dependent quantity. That's why the question also says relative to a reference frame, right? Relative to a reference frame, because the same rod, if I move the axis here, right, so the inertia changes. About this, the inertia becomes 1 by 3 ml square, right? So the inertia is dependent on the reference frame, and what we have seen till now is that if there is a world frame, which is the inertial coordinate system, and there is a rotated frame, right? Let's say this is the A frame and this is the O frame, right? So transforming from the a vector from the A frame to the world frame is done like this by multiplying by a suitable rotation matrix, right? But for this inertia tensor, right, for matrices, the transformation takes place something like this. So it will be, let's say this, the frames are the same, and I want to transform inertia matrix from this A frame to O frame, right? So it will be something like this. So you multiply on both sides of the, one side with the R and another with R transpose. You multiply on both sides of the inertia tensor. And you have to be a little bit careful here, in the, because switching the order of R and R transpose will either take you from the base to the world frame, or the world to the base frame. Base frame, I mean that this A frame, right? So you have to be a little bit careful, but transformations happen like this by pre-multiplying and post-multiplying by the rotation matrix and its transpose. We can transform inertia matrices from one frame to another frame. All right, and yeah, so this was about the diagonal terms. The off diagonal terms, let's say IXY, right? So that is calculated again as a volume integral, but the expression inside is different. It's something like this. So again, a product of two coordinates. So here the squared distance squared term will come, and here is the mass term. So similarly, IYX, here would be yx times rho dv, and Iyy will be x square plus z square times rho dv. Okay, so inertia matrices are widely used because in order to solve the dynamics of a rigid body system, we will need the mass distribution of the manipulators or the links of the robot, and inertia matrices are used for that purpose. So very fundamental for robotics. Okay, next question is, in the Newton Euler method, the outward iterations are used to find which quantities, right? So this is the point which we had stressed quite a lot in the previous discussion R, that the outward iterations, we get the forces acting on the CG of the link, right? So this is the correct answer. Not only forces and torques or moments on the CG of links. Right. This is what we got when we did outward iteration of the manipulators, and the relevant equations are Fi is equal to m v dot ci and ni is equal to ci I omega I plus omega I cross ci I omega I. Alright, so this ci here is important to note, that ci is the reference frame at the center of mass. Okay, so you see that reference frames are very crucial. Just excuse me for a minute, there is a delivery call that I need to take. हेलो हेलो भैया, आप कहाँ पे हो? हाँ, आप कहाँ पे हो भैया? नॉर्दर्न लैब 1, डिपार्टमेंट ऑफ मैकेनिकल इंजीनियरिंग। ये आप गेट से घुसिएगा, कारगिल चौक है, कारगिल चौक से आप लेफ़्ट लीजिए, राइट लीजिएगा तो ऑडिटोरियम आता है, ऑडिटोरियम आता है तो वहाँ पे गेट है एक, देखा होगा। तो उस गेट पे सिस गार्ड, वहाँ पे गार्ड रहेगा, गार्ड से पूछ लीजिएगा डिपार्टमेंट ऑफ मैकेनिजिंग, वहीं से पास में ही है, जस्ट घुसते ही तो बता देगा वो आपको। ठीक है, नहीं फैकल्टी यूनिट से और पहले ही है, थोड़ा फैकल्टी यूनिट से पहले ही थोड़ा एक गली कटती है राइट साइड पे ही, तो उसमें ही है। हाँ हाँ हाँ, वही 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 वही। हाँ, और मैं आपको एक नंबर एसएमएस करता हूँ, एक्चुअली मैं एक मीटिंग में हूँ, आप उस पर कॉल कर देना। ठीक है, व्हाट्सएप कर देता हूँ आपको। ठीक है, ओके भैया, ठीक है। हाँ विनाश, मैं आपका नंबर एक डिलीवरी वाले को दे रहा हूँ जो एक्चुएटर्स लेके आ रहा है। मैं अभी इसमें क्लास में हूँ तो मैं रिसीव नहीं कर पाऊँगा। ठीक है। हाँ, वो अभी टाइम लगेगा, वो कॉल करेगा आपको। ठीक है। Sorry for that. So, yeah, we were discussing the outward iterations of the Newton-Euler method, and they give us the forces and moments on the CG of the links. Okay, so moving on. Any doubt in these expressions from the last class?
Sir.
Yeah.
So here they have said CG, no sir. CG means center of gravity, no sir. But we are talking about center of mass. So how are they equal, sir?
Yeah,
Like
so in case like the gravity does not vary across the length of the or across the dimension, any dimension of the object, then CG and COM coincide, right? CG will vary from the center of mass when the gravity vector varies along the length of the or any dimension of the body, which is not practical for bodies at the scale at which we work on. It would be like, a rod which is comparable to the radius of the earth or something kind of like that. So for all practical purposes, CG and COM are the same.
okay, sir. Okay.
Yeah.
So,
Mm-hmm. Go on.
what about momentum
Momentum
of the
of
link? Of the link, like how that one is.
how that one is calculated.
No, how that one is not coming in outward
Okay,
iteration.
not coming in momentum of the links. Momentum of the
Yes.
links, yeah, like you can say that they are there because we have the velocities already, right? And we have the masses of the links. So momentum of the links is available to us, I would say. But in that Newton-Euler method, like the precise sort of an algorithmic way of solving dynamics, the intermediate outcome that we get after the outward iteration, which we use in inward iteration, are the forces and moments on the CG or center of mass of the links. So momentum will not help us solve the next part of the problem, which is the getting the joint torques. But yeah, at this stage, after doing the outward iteration, you because you have the velocities and you know the masses of the links, you would also have the information about the momentum of the links. You are right.
Thank you. Sir.
Okay. And subsequently, the next question is about the inward iterations, which are used to find the final outcome of the dynamics, which is the joint torques. So, let me just also rewrite the inward iteration expressions, which use the capital Fi and capital Ni, which we got after the outward iteration. So, this is the force balance equation for a link, and the second part would be the torque or moment balance. So again, the point to note here is that on the left hand side we have torque about the center of mass. So on the right hand side we need to express the distances with respect to the center of mass of the link. That's why you see the subscript in the distance, that is the position vector. This is ci. So basically we are writing everything with respect to the center of mass of the link. Cross fi plus 1, right? So torques due to the two forces at each end of the link, the two reaction torques is equated to the moment at the cg. Okay, so doing the inward iteration steps, one by one gives us the joint torques, which are these quantities, the small fi and small ni. Okay, now the fourth question says
So your voice is breaking, sir. Like,
okay, the fourth question says any part that you missed in the third question?
sir, I want a small clarification, sir.
Yeah, go ahead, go
Uh,
ahead.
the, in the previous session, sir, we discussed that f when we say small fi, sir, is the force applied on link I by link I plus one? We discussed, no, sir, by the definition. It is
I
the force
think
that is applied on link I by link I minus one.
yeah, link I by on link I by link I minus 1. Yeah, right.
Uh, but sir, when we did static analysis, sir,
Mm-hmm.
uh, uh, we said that if while doing that static analysis, like week 4
Mm-hmm.
session discussion, sir,
Mm-hmm.
while doing this for static analysis, we discussed about a 2-hour planar manipulator where a force of F is applied at the end effector, sir.
Mm-hmm.
At that time, we discussed that the higher joints, that is joint 3, joint 2,
Mm-hmm.
joint 2 is the, I mean, the force acting at joint 2 creates the force acting at joint 1, no, sir. But this is contradict it con this like here this contradicts with that, no, sir. Which one is correct, sir? uh,
Hmm.
like here the link I minus 1 is creating I force. I mean, fi minus 1 is creating fi force, but over there fi plus 1 is creating fi, no, sir.
Yeah, I mean, the confusion might be on two levels. One might be due to the notations, which I think are consistent to what we discussed that week, and so that part I would be less worry about, because if the confusion about notations, then we can always check, go back and resolve it. But let's try to understand what happens like physically. Okay, so these links are connected together, and let's say in that case you say that, or we saw that we are applying a force on the end effector. So when we apply a force on the end effector, and uh, we also assume that the link is in a static condition, right? So there, let's say if there is gravity acting, then there would be holding torques acting on the joints. If there is no gravity, then the joint will be there in a, the manipulator will be there in a certain configuration. Okay, so let me just draw it. So the forces come due to the fact that the links are, as I think mentioned this approach of thinking in the last class also, that always try to think by taking out these links individually, right? So every link is applying a force on each other, right? That's the Newton's third law. Okay, so if I isolate this link, the second link, right? So a force is being applied here, which is F, the external force. Let me say this is the external force, right? And there will be a force vector at this joint also, which is, let's say, the unknown. Okay, now when I draw the free body diagram of the first link, then I apply an equal and opposite force on the first link, right? And I apply a force here. So let me put this as, again I am adding some notations. I can put it as FB. Let's say FB here and FB here also. And here I will again put a force in some direction FA, right? Which is the force. Let's say if there is a hinge here and I draw the hinge also separately, then it's the force equal and opposite acting on the hinge. So the what I am trying to motivate here is that uh, notations can vary. I might have also switched them somewhere, someplace in discussion hours, but the always fall back to the physical understanding of the setup, right? There are rigid bodies connected, by revolute joints, and whenever there are forces acting, you take out each link individually and you draw, or not draw, you apply forces at each of those connections. So, or that those are forces at the joints, and if there are any other external forces, right? So this way you won't be confused, because forces are being applied by every link on the other link, right? Link I minus 1 is also applying a force on link I, and link I is applying an equal and opposite force on link I minus 1, right? Is that point clear to you?
Yes, sir.
Right. So that's the physical part. Is the physical understanding is up till that only, that let it be 3 hour 4 hour manipulator, an arm manipulator. If I isolate this link, right, this link I isolate, and there are no other forces acting, so the only two forces acting on this are at the at this joint. Let's say this is joint I, and this is I plus 1, right? So there will be a force acting here, and there is a force acting here, Fi plus 1. That's what I only I only will be concerned about, right? And similarly, the adjacent links, if you draw, right, let's say the next link you draw, then you apply an equal and opposite of this Fi plus 1 here also. Why I say always equal and opposite? Because the link is not breaking. In all these analysis that we do, the link is not, it's not that they fall apart. So the forces will always be equal and opposite to each other. And similarly about torques also. So similarly you will apply some joint torque here and some joint torque here, and that's what we are doing. Basically these links are being connected in a sequence, and at the both ends of the link, if they are connected to another links, there will be forces and moments acting. That's the very fundamental understanding of it. The way you number it, the way you keep I plus 1, I minus 1, that's all construct, in order to make you understand, and also take it towards implementation of a way of a program, because finally we need to program these things. So let's say you are writing some loops, where you can use them as indices and all. So that's where these things come in. But the very basic picture is just this, that there is a link, you isolate it, wherever it's connected to, you apply forces and moments, and if there is any other external force, you apply that too. let's say if let's say if this this end effector is holding something, some object it's holding. So we and if you draw the free body diagram of this final link, then you will add a force here, that there is a force, the weight of the object, let's say mg, acting on here. And at this end, at the joint, again you will draw some force which you will need to compute, and some moment which you will need to compute. Does that make things clearer, Karthik?
Yes, sir. Yes, sir. Got it.
So always try to think from the first principles whenever whenever you feel that you are getting confused. Always try to fall back on the very basic understanding, and that will always help you again re-understand these equations and all, even if the notation sometimes confuse you. Okay.
So
Yeah, go ahead.
At first, when we balance force, some imbalance in moment is created. So that for that we solve in the next step, isn't it?
No, it's not like that. It's not like that. Is that to get the to solving for the force balance, we don't need any extra information, and for solving the moment balance, we do need the force information, right? So we can't solve for the second equation before the first equation, because second equation needs this fi's and fi plus 1's. So first we solve the force balance. Force balance just need these two forces. So fi plus 1 will be known because we are doing inward iteration, right? So we are moving from higher joint to the next lower joint. So I plus 1 will be known. From the outward iteration, this capital Fi is also known, which gives us the small fi. So first equation, every equation when you formulate, you have to make sure that there is only one unknown there, which you will find, right? One unknown vector. There can't be two unknown vectors in the same equation. So that's the reason. Like the first equation, you have one unknown vector, you solve it, you get the information about fi. Then in the second equation also, then you know fi and fi plus 1 both, and ni plus 1 also, because again inward iteration. So the only unknown remains small ni, right? So again only one unknown, so you solve the second equation also.
Okay, sir.
Okay, so it's a very again it's a very programmatic way of doing things, and if you stick to this order, it's bound to be correct. Okay, yeah, it's good that you are asking more questions now. All right, so the fourth question says the Newton-Euler method is a which type of method? Either it's a force-based method, energy-based method, and two other options are also there. And we saw that since this strategy involves forces and moments, so this is classified as a force-based method. And its companion is the other approach of finding equations of motions and relating forces and torques to accelerations is the Lagrange Euler method, which is a energy based method. So in the Lagrange Euler method, we define something called as the Lagrangian of the system, which is the difference of the kinetic energy and the potential energy. And kinetic energy will be the sum of the kinetic energy of all links. So if there are n links, then 1 to n. And similarly, potential energy will be sum of the potential energy of let me denote the u. So yeah, so the methodology of generating or deriving equations of motion using the Lagrange Euler method is to first write the expression for the kinetic energy, write the expression for the potential energy, find the Lagrangian, and then again put it into the final Lagrange Euler equation, which is d by dt del L by del theta dot I minus del L by del theta I is equal to tau I. And the index I is very important because you do this step, putting the values in these equations and taking derivatives and time derivatives. You do this for every degree of freedom, right? I is the index 1 to n, which denotes it's a n link manipulator, so n degrees of freedom or n joints. So you write this equation for every degree of freedom, because this tau I is what is called as a more formal term. We are calling it torques, but more formal term is generalized forces. And generalized forces are the forces which act on those degrees of freedom, right? So for a, let's say, 3R arm, right, 3 joints. So in this case, the generalized forces vector would contain tau 1, tau 2, tau 3, 3 joint torques, right? Similarly, if there is any prismatic joint, then again a force would be there, right? So you have to write this for every degree of freedom, not just for a single one, or not together for all. So for small systems, you can do it manually also, but for more higher degree of freedom systems, you might need the help of a computer to generate those expressions of, because the process of taking derivatives becomes very tedious and it's prone to mistakes. Okay. The sixth question says, in the Lagrange-Euler method, a scalar function called Lagrangian is formed that is equal to the, as I just mentioned, the difference of the kinetic energy and the potential energy of all the links. So sum of the kinetic energy for all the links, sum of the potential energy for all the links, right? So this is the L is equal to K minus P. Okay. Okay. So this question pertains to finding the kinetic energy of a link in this 2 degree of freedom manipulator, and note that it's not the usual 2R manipulator, but it's a RP manipulator, that is, it's a revolute prismatic manipulator, right? So this is revolute and this is prismatic. Okay, so the order denotes that the first joint is revolute, this is the revolute joint, and this is prismatic joint, right? So the first link can rotate about z0 or z1, and the second link will translate along z2. Okay, so recall the dh parameter convention. We keep the z axis along the degree of freedom. So first is the revolute joint, so z0 and z1 are along the same direction, but z2 is a translation, so prismatic joint, so it's along the direction of that translation. Okay, and a few inertial parameters are given, that is, m1 is the mass of the first link, which is shown concentrated at a point. Again, m2, this is also a simplification, an assumption, right? Because in reality, for practical bodies, the mass is distributed, right? So the mass distribution or the inertia is not as simple as this. This is like approximating the link as just a point mass located at the center of mass. So the link lengths are, the first link is L1, and the joint variable for the second joint is the translation distance d2, not theta 2. So the joint variables are, joint variables here are theta 1 and d2. Okay, so what you need to do is formulate or write the expression of the kinetic energy in terms of the derivatives of the joint variables, so the joint rates. So joint rates would be theta 1 dot and d2 dot, right? That's the, so for the first joint it will be angular velocity, and for the second joint it will be a linear velocity, right? So that's the scene here. And this question, it asks the kinetic energy of the first link, and it's given that izz1 is the inertia of the first link, so inertia is given. Okay, and why izz only? Why izz? Because rotation of joint 1 happens about z axis, right? So since z is the axis of rotation, the only inertia that we are concerned about is izz. Okay, so kinetic energy is the sum of translational and rotational. The translational part is given by half mi v ci square. Vci is the velocity of the center of mass. Okay, plus half I zz. First I will write omega I square. Okay, now we need to get these quantities. Okay, mass and inertia we have, we need to get vci and omega I. So how will you calculate vci? Vci is the velocity of the COM. So V1 for the first link, velocity of the center of mass, is, how to write that? So recall that it's a point mass rotating at a angular velocity of θ1 dot, right? And at a distance L1 from the origin or from the axis. So what's the velocity there? The velocity is omega cross r, and in this case it will be θ1 dot L1, right? This is the velocity of the center of mass of the first link. So the translational kinetic energy will be half m1 θ1 dot square L1 square. Now the rotational part. So the rotational part, the inertia is given and the angular velocity of the link, since it's the first link, right? So angular velocity is same as the joint rate of the first joint. So θ1 dot square, right? So this is the kinetic energy of the first link. Okay, so the answer comes out to be half m1 L1. Okay, so first term is the same in every one. So the second zz1. So this is C, right? Any doubts in calculating kinetic energy?
Sir?
Yes, Karthik.
Sir, here when izz is given, here when we write the inertia tensor, sir, there how are the product moments are equal to 0, sir, for this case, for the link 1? How are the product moments 0, sir?
Yeah, so you can try to think of it in this way, that okay, so since you have asked specifically about inertia, let's draw this thing separately. Let's draw it here. There is some space here. So how is link 1 shown? Like link 1 is shown like this, that all the mass is concentrated at the center of mass, right? And also now let's see the axis. What are the reference axis? So you note that this is IZZ1, right? So IZZ, that is the inertia about the principal inertia about the z axis, and it's in the first frame of reference. Okay, so that is the reference frame 1. Okay, so in reference frame 1, z is like this, about which it is rotating, z1. Okay, along the link will be x1 by convention, and perpendicular to both, that is y will be, to maintain right hand rule, y will be here, right? So now see, what's the, you asked about the I, let's say the xy term, you know. So what is this? This has the product inside x into y, and then rho dv. Okay, this is xy. So you see that the only mass that is shown, or we have framed it like if all the mass is concentrated at the COM, right? So it's a point mass. It's just denoted for as extended purpose, but it's a point mass, and its coordinate is what? L1 comma 0, right? So the y coordinate is 0 always. So this term will always vanish. There is no distribution. You can also always also think like there is no distribution here. There is no distribution here of the mass. The mass is only at a fixed distance L1 along the x1 axis. So terms involving y will also vanish. And what could be the other terms? So xz, right? So xz will involve the product of x and z, but in z direction also there is no, the coordinate, if I write in 3D coordinates, it's, so z is also always 0. So terms involving z and y will always vanish. So xy, xz are 0, and the only term that remains in yz, and yz involves y and z, so they are also 0. So all of diagonal terms are 0 here. Did you get it, Karthik?
Yes, sir. Clear, sir.
And similarly, the two diagonal terms also, that is Ixx, right? Ixx was the volume integral y square plus z square, right? Which is again 0. Iyy, which is x square plus z square, right? And Izz, which is x square plus y square. So the only two non-zero terms here would be these two terms, Iyy and Izz. And both will be same because z and y are 0, so both will be the same. So which will be some value, right? And the value will be m1 L1 square, and this is also m1 L1 square, right? Because this is the very basic when you first studied about inertia, that a mass m kept at a distance L from the axis, then what's the inertia of this mass? ml square, right? Which is the case here also, that if, so Iyy corresponds to rotation about the y-axis. So how is the mass distributed about the y-axis? This is the y-axis, and the mass is a distance L1 from the y-axis, right? So the same scenario as this, and the inertia will be m1 L1 square. Okay, from the z-axis, the mass is distributed precisely at L1, right? So point mass at a distance L1 from z-axis, inertia will be this. Okay, and along x it should be 0 because the mass is itself on the axis, right? So there is no distance, it's on the axis itself, so distance is 0. So about x it should be 0, and it is 0 in fact. So if you want to write the full inertia tensor in the first reference frame for this link, it will be 0, 0, 0, 0, 0, 0, 0, and two non-zero terms only, which are this IYY and IZZ. So this is the inertia tensor of the first link. I think it should be much clear now.
Yes, sir. It is clear.
Okay, so that's how for simple situations you can geometrically you can visualize also, like why something is 0 or why something is not 0. All right, so the next part of the question is question 8 is the potential energy of the second link. Okay, so whenever you are writing potential energy for any system, the first thought which you should come to your mind is where is my reference, right? Potential, wherever you study, whether it be gravitational potential, electrical potential, to define potential you always need a reference. Okay, because let's say and the reference could be arbitrary. So for potential energy, first decide the reference. Always do this, right? So reference is the, where you say that this is my 0 point, this is from where I am measuring the potential, right? So in this case, the way the options have been given, right? So and there is one more quantity here, d2 max. So d2 max is the maximum extension of the second link, right? So you can think that it's this joint is there in which the second link is there, and the maximum this link can come out is, and the distance from the center of mass would be here, so distance is d2 max. Okay, so the way the options have been framed here, you can conclude from that the reference position is something like this. If this is the hinge, if this is the hinge, then the reference position is when the links are like this. This is the first link, COM here, and this is the second link, COM here, and this is at maximum extension, right? So d2 max, right? So this configuration, this point, in this point we have defined that P2 is 0. Okay, this is the reference, and once we define this as a reference, then we can write the expression for the potential energy when the position of the link is like this, when it's t2 here and rotated by theta 1, right? So what will be this distance? This is d2 sine theta 1, d2 s1, right? And this distance will be d2 max. Okay, so p2 in this configuration will be from reference, which is 0 plus mgh. So m, g and h. What is the h from the reference? It's d2 max, first d2 max, and then extra d2 sine theta 1, right? So this part will be the potential energy of the second link for this reference, and it matches to, I think, the third option, right? m2g d2 sine theta 1 or m2g d2 max. Any questions in potential energy computation? Okay, the potential energy is usually much straightforward. The only yeah, The only catch there is that you should choose references always, and sometimes references should also be that it simplifies the problem somewhat. So when you solve more problems, you will see that some references lead to more simpler or simpler expressions for potential energy than some other choice of references. So that's a choice which comes when you solve more questions like this. Okay. The ninth question is the dynamic equation of a serial manipulator is what type of a equation, right? So first let's write the general expression, right? So the generalized forces are related to the inertial properties of the manipulator, like this, right? The most general rigid body dynamics equation. Okay. Right. So this is the inertia matrix. This is the Coriolis and centrifugal terms, and these are the gravity terms, right? So, and of course, since derivatives are involved, so this is definitely a differential equation, so that checks out in all of the options. Then the second layer of difference is whether it's coupled or non-coupled. So definitely it's coupled because it cannot, like, you cannot separate out different joint variables out of these equations, right? You cannot write separate equations without any further simplifications, of course. You cannot write always separate equations for each joint. So it's a coupled differential equation. All the variables theta 1, theta 2, they are coupled, they are multiplied together. And since they are multiplied together and there are, you know, square terms involved, degree is involved is more than 1, so it's also non-linear. So it's a non-linear coupled differential equation, right?
Sir,
Yeah.
can you, can you tell what is coupled and
Yeah,
non-coupled?
coupled I will tell you. So let's say let's say for a system you can write the dynamics like this, that theta 1 double dot is some m1 theta 1, and theta 2 double dot is, let's say, some constant k, right? Or let's say, like, I will put theta 2 here, or like c theta 2 dot. Okay, so in this you can separate out equations which just involve variables corresponding to only one joint, right? So basically you can treat them as separate, like this is the equation for joint 1, this is equation for joint 2, right? There is no coupling, that is, there are no terms in which these thetas are multiplied together, like these terms like these. Okay, once terms like these appear, then we say the system is coupled, and this itself leads to a nonlinear system. So once terms like these appear, it has already become a non-linear coupled system. So coupled means two variables are together in an expression, that is coupled. So if there is an equation like this, xy plus 2 is equal to z, so right, so this is a coupled term in xy, you can't separate them out. So that's what the meaning of coupling is. When you write, even as for a 2R manipulator, if you write the expression of mass matrix or Coriolis terms, you will very quickly see that theta dots are getting multiplied for both joints. So it it quickly becomes a coupled differential equation. And if you want to make your life simpler, then you know add some simplifications. Let's say use some usual simplifications, because dynamics equations, if, and especially for increasing degrees of freedom, they become solving the full dynamics like in this form, it becomes very computationally expensive, right? So to solve the dynamics on a robot which has a limited computational power, right, we take lot of assumptions, right? So many a times you would see that the Coriolis and centrifugal terms are altogether ignored, with assumption that, let's say, the speed of the robot or is not that high, or some way somehow the physical structure is that these terms are not very, they are very small compared to the inertial terms, right? So lot of assumptions can be brought in order to make our life simpler and lead to, let's say, non-coupled systems or linear systems. Linear is more or less very less like you need lot of assumptions. For some simpler systems you can get, but for practical robots like humanoids and all, it's very difficult to get linear systems. And if you simplify your systems a lot, then you lose a lot in what kind of motions that you can perform on that robot. So your freedom goes down once you reduce the dynamics to a very simple form. So that's a trade off, like how much you can compute, or how much you are willing to sacrifice in terms of motion generation capability. So yes, I mean that's a little bit practical viewpoint of solving these dynamics equations. And finally, the last question says the total dynamic equation is made up of, and we are already discussing about that only. So it's the inertia, Coriolis, centrifugal, and gravity terms. So inertial. So whenever you will read inertial effects or inertia terms, it's to do with the mass times acceleration term, and mass times the double derivative terms. That's the inertial term, right? The second term is the, as I mentioned, which involves the Coriolis and centrifugal effect. So that's the second component, and the third component is the torques or forces that come due to gravity. And all these terms like mass matrix, all of course will depend on the configuration of the manipulator, because as the links move, uh, the mass matrix would change, right? So yeah, I mean that's why we show it as a function of the theta. Okay, so yeah, we finished discussing the questions of dynamics, manipulator dynamics. And before we move on to trajectory generation theory, which I will discuss in the remaining time, uh, any other questions?
Sir,
Hmm.
we call this the RP manipulator, which I'm sorry, not RP manipulator. We call serial manipulator because all the links are similar, sir.
Not similar, but the links are connected one after the another, right? So
Okay.
yeah, it's a good question. So serial manipulators are like there is a first link, then a second link, then a third link. So each link is connected to at max two links, right? The end link will be connected to only one link. So at max each link is connected to two links. There is no branching, right? It's not like something like this. Once I do this, this does not remain a serial manipulator, right? So as simple as that. Like you add in sequence, it's serial. You branch out, it becomes parallel. Yeah, very good example, Vaibhav. Yeah, that's a great example.
Yes, sir. Got it, sir.
Hmm.
Sir, then in middle, why do we say the dynamic serial manipulator, sir? Like
Dynamics?
we are unable.
Can you repeat it?
Dynamic serial manipulator.
The dynamic equation of a serial manipulator. Yeah, okay.
Uh,
So,
yeah, not this. Dynamic. We say no, so dynamic serial manipulator. What does that mean then, sir? What does that?
dynamic serial manipulator, like, I'm not sure if that adds any new information. Like, uh, a manipulator is to move, and right, and when you move, the dynamics is always involved, right? So, I don't think that adds any new information about either the manipulator or dynamics. It's not sure. Did you see that the term somewhere, or did I use it?
No, no, no. You didn't use, sir. I have seen it when I was reading an article, sir. That's why I
Okay.
asked. It is
Yeah, maybe
related to
like
it. So,
dynamics sometimes, if it's not precisely a textbook or a technical course, dynamic can be used as a general term also, right? A dynamic means that something which moves quickly or fast, a dynamic person, that kind of it can be used in a very generic context also. A dynamic senior manipulator might mean that a senior manipulator which is moving fast and doing quick actions. Maybe that would be the meaning. Not sure, not sure.
okay, sir. Okay, okay, okay.
Yeah, so now let's move on to, since we are, as I just mentioned, manipulators we design in order to move, right? And in order to move, we need to send some commands to the motors, right? And of course, we would not like to move these manipulators in any arbitrary way, haphazardly. So the robots joints will move with some purpose, right? In order to make some progress, either move towards a target or pick something, place something, or if it's a mobile robot like a humanoid or a quadruped, move from one place to another. So the idea is that a lot of a lot of engineering goes into how to move those joints, at what rates to move those joints, and then finally the last piece is how to control those joints or follow those desired trajectories. So first let's discuss few terminologies, right, which will continuously pop up in our discussion. First is trajectory, the word trajectory itself. So whenever in the context of robotics you hear trajectory, so trajectory means that you have information. So trajectory, saying trajectory, you visualize a path, right? Always it comes like a path, right? So in daily discourse you see, let's say you're watching some sports, you say trajectory of the ball, so whenever we say trajectory, a path comes to in our mind. But trajectory does not only involve position information, but it also involves velocity and acceleration also for each degree of freedom, right? So once I say that I have the trajectory, or I have planned the trajectory, then what I am communicating precisely is that I have the position, I have the velocity, and I have the acceleration also, for that degree of freedom or for that joint. So I have that data, I have that planned. Okay, so trajectory basically encompasses all three information, right? So that's the first thing. Second is two terms which are very common and sometimes used interchangeably also, and the difference is not very stark, but I would like to again point out. So what's the difference between path planning and motion planning? I would just give you a chance to just, maybe if you know, or you can just think out. Can any of you just give some
In
idea?
motion planning, you are considering timing also.
Okay, and in path planning?
You just want to move around from one place to another.
Loosely, yeah. I
Like
mean,
catching a ball should be a motion planning, and picking and placing an object should be path planning.
I would not entirely agree to that, because every you do path planning, uh, you know in most of the cases both of the things are involved, right? So it I won't say it you say that you as you said that catching a ball is motion planning and picking and placing is only path planning, like just categorizing both either of them in separately. uh, I won't describe like that. So let me put it like this, that so the point regarding the way we want to move around, which you described, is loosely what is path planning. It's basically, whenever we say path planning, we mean the high level manner in which we want to move, right? So let's discuss this with example of a robot. So since I work on legged robots, I will take example of a legged robot, a quadruped, right? So a quadruped robot, which, let's say for this very simple case, it's a planar quadruped robot which has, let's say, four joints. Okay, four joints it has. And let's also draw some environment. Okay, so let's say this is the starting position, this is the goal position, and maybe there is some forbidden areas where if it steps, some ditches are there. Okay, now when I say that I have solved the path planning problem, right, then the only what suffices or what is sufficient is that I have a path connecting the start point and the goal point, which is collision free, right? So it's a it's feasible, or you can write collision free, or whatever, like free from these obstacles, no obstacles. So it's a path that on which if would move, you would reach from A to B, right? Now when it comes to motion planning is a lower level thing, right? It comes after you have planned the path. So motion planning is, you think on the joint level, right? So for this four joint quadruped which I have drawn here, when I would say that I have done motion planning for this and for this given path, then the information that you would expect out of me is that I can give you how each joint should move. What is the trajectory of each joint for this entire motion from A to B. Yeah, so that this path is traced, right? So it's like moving from A to B. In order to move this exact robot from A to B, what are the trajectories that you would give to each of the joints? So that is the domain of motion planning. So we start from path planning, and somewhere we transition in between to starting to think about how to move the actual robot on this path, and then we say that we have now shifted towards the motion planning thing. So the example that you said, the pick and place one, so of course pick and place one, I'm assuming you are doing with a manipulator, and right, and of course there would be some obstacles, some constraints. Let's say if you are picking a object from a table and putting it on the table itself, then there is need you of course, if there is no obstacles, then the path planning problem is much simpler. There you just move vertically, move some horizontally, and then move again down vertically. Let's say very simple path you planned. So that would be the path planning part, but the motion planning part would be how much each joint moves, right? What's the trajectory I have fed to each of the joints in order to execute this path. So both activities happen anytime you basically move a robot or a manipulator, right? So the difference is that at which level we are thinking. So path planning is high level, where you are just concerned that you treat your robot as, just maybe as a kind of a black box, a cuboid, let's say, and you're just concerned that this cuboid just passes through, right? You plan a path like that. And the motion planning is where you think at the joint level trajectories, right? So Karthik, is your network unstable?
Yes, sir. It's a bit unstable, sir. I joined, sir, not came. Yeah,
Okay,
yeah.
did you miss any of these parts?
No, no, no. I heard, sir. Just
Okay,
a few seconds I missed.
okay.
Yeah, I.
So once that we have this out of a way, path planning and motion planning, so yeah, the point of spending some time on this is that I would like you to, when to use these terms wisely and not loosely, to use them interchangeably. when you, because a path planning problem, because that has some effects on, what actual computations that you do. Because path planning problems, you would generally work on algorithms like which find obstacle free paths in a map, right? You won't consider much about the dynamics of the robot, right? So you will work on algorithms like a star, rrt, if you have heard of these algorithms. That will be in path planning problems. In motion planning problems, you will work more closely on the robot, right? You would be concerned about which type of robot do you have, what are its constraints. You will plan the actual locomotion there. So again, these lead to two different verticals of work also. So it's good that if you know the difference on, let's say if you wish to communicate to someone that I'm interested in path planning or motion planning, then so you should be aware that what comes after it. All right, so okay, we want to plan out trajectories which have the position, velocity, and acceleration information for each degree of freedom. So trajectories we can plan in two ways. And two ways, I mean two spaces, and these are the same two spaces which we have seen time and again. That is the joint space and the Cartesian or the task space, right? So joint space, you plan theta, theta dot, theta double dot. Cartesian space, you plan x, x dot, x theta dot. In Right, first you do in this, like finally you would have to go in terms of the joint variables, which for a revolute joint is theta only, right? But at the initial stage, you work in the task space, not in the joint space directly. So that's the Cartesian planning. And we will see what are the some shortcomings of each of these approaches. All right, so let's take an example in which, you know uh, we have a 2-hour manipulator, and let's say we want to move from this position to this position. Okay, so no, let's say you have this setup in front of you. You can feed commands to the motors. So what are the informations that you would need, right? So the setup is that it let's call it as configuration A, and let's call this as configuration B, right? So we have to goes from this manipulator goes from A to B So, and other information we can take is, let's say, starts from rest and ends at rest also, right? So what information does this give is that the joint velocities and accelerations, all of them are zero, right, at the beginning and at the end. So theta, this is theta 1a, right, and this will be theta 1b. Similarly, this will be theta 2a, and this will be theta 2b. Okay, so what information you would have is the theta initial, theta end, theta dot initial, and theta dot end. Okay, so four pieces of information you generally have. Just a second. Okay, so once you have this four values, a very common, now what could be the choices of trajectories? Sorry, it could be linear, it could be quadratic, it could be cubic, or some other higher order polynomials. So general choices are polynomials or sinusoids, right? So what are the things that we will look when you know choice? A very obvious thing would be to, you know what are the velocities and rates that we get. We don't want to go a trajectory which has a lot of sharp changes, or a jerky trajectory. We would want the trajectory to be smooth, which changes values gradually, not rapidly, right? For most practical purposes, sometimes it might be necessary, but generally I'm speaking. Right, so, and a very common choice is the cubic polynomial. So degree 3. Okay, so a general, so what is, and what do we describe by the cubic polynomial? The position, the joint angle. So the joint angle we describe as a cubic polynomial. Right, so cubic polynomials, if again, if you take derivative with respect to time, it will come out to be a1 plus 2a2t plus 3a3 t square, right? And again, if you take derivative for the acceleration, it will come out to be 2a2 plus 6a3t, right? So what you see is that by choosing degree 3, you get time information in all of those. So you have the ability to change all the three: position, velocity, and acceleration with time, if you choose a cubic polynomial, right? If I choose a quadratic one, right, if I choose a quadratic, which is a0 plus a1t plus a2t square, then the first derivative will be a1 plus 2a2t, and the second derivative will be just 2a2, right? So it will give me a constant term in acceleration, right? So I would not like to have a constant acceleration always, right? And linear is again, it's even much simpler. It's like it will be constant velocity and zero acceleration. Okay, so to have more dexterity, have more freedom of shaping the trajectory, you choose higher and higher degrees of freedom. So in practical purposes, people use like fifth order, fourth order, and fifth order trajectories for generating motions. So, and the idea behind it is also that the more the degree of the polynomial, the more freedom you have to in shaping your trajectories. So it becomes really important when you have obstacles in your environment, or you have to do complicated maneuvers. So you can have more curvilinear kind of a trajectories. So basically increases the dexterity of the manipulator. So but cubic lies in a very sweet spot. It gives this freedom also, and it has like only four unknown variables. So the variables number of unknown variables is also manageable, right? So the unknowns here are the unknowns are a0, a1, a2, and a3. So four unknowns. So we would need four equations, right? And where do we get them? Because we have four boundary conditions, like four boundary conditions. What are the boundary conditions? We have that theta at 0 is, let's say, theta 0, theta at time tf is theta f. And first we will consider the case of starting from rest and ending at rest only. So theta dot is 0 and theta dot at the end is 0, right? So what you do next is basically use these boundary conditions. So these are what you are putting values of t in the expression of theta t, theta dot, right? So theta 0 will give you equation theta 0, put t is equal to 0 in this. So equation will be a0. So first equation is a0 is equal to theta 0. Second equation, let me number it here also. First equation, second equation, third equation, and fourth equation. So second equation is you put tf and equate it to theta f, right? So second equation will be a0 plus a1 tf plus a2 tf square plus a3 tf cube is equal to theta f. Okay. The third equation, you need to use the expression for theta dot. So first you will put t0 in this. So it will give you a1 0. And finally you would put tf in it. So it will give you a1 plus 2a2 tf plus 3a3 tf square. So a1 plus 2a2 tf plus 3a3 tf square, and this is also equal to 0, right? So what you, and this is the same process you will also take if for any boundary conditions, not just for 0. Like in place of 0 you will write some theta 1 dot, sorry, theta 0 dot, and in place of here you will write some theta f dot, right? So it's the same. So you get four equations. So four equations, four variables implies that you have a unique solution, right? So, and the solution will give you the four parameters of the cubic polynomial, and once you know these, you can plot them, plot the velocity, plot the acceleration, right? You can do all sorts of things. So the expressions for those the a1s, a2, a3, a0, those have been derived in the lectures also. You should derive them by your own hand also once, right? And again, pretty much straightforward, right? So cubic is,
Sir,
yeah.
uh,
Yes, Karthik.
can you just repeat once again, sir? Why after that, after writing a1 is equal to 0, comma theta 0 dot
Yeah,
theta dot,
so
why you?
that is the case. So that is the case in which the velocity boundary conditions are like this: theta dot 0 is theta dot 0, some non-zero velocity at the beginning and some non-zero velocity at the end, right? This is the general case, right? Taking the velocity 0 at the beginning and the end simplifies the computation a little bit, but you can take it non-zero also, some theta dot 0, some theta dot f. So in that case you will not equate it to 0, you will equate it to that given value, or you will equate it here also to that given value, theta dot f, right? So that's just the difference.
Yes, sir. Yes. Okay, sir.
Okay. So
Okay, sir.
yeah, you will get four equations, four variables. You can solve it, and usually you won't solve it by hand. You can either use the closed form expressions for a0, a1, a2, a3 which have been derived, or you can also use some tools like MATLAB and all to solve this very quickly, almost instantly you can solve. So yeah, so planning cubic trajectories is very straightforward. Now, another common type of trajectories that are used is something called as linear function with parabolic blends, right? Linear function with parabolic blends. So let's just look at this and then we will close for today. So the motivation here is that sometimes we can use linear trajectories, but linear trajectories, if we just use like this, then at the starting and at the end they will always have non-zero velocities, right? So if we let's the manipulator is at rest, then the trajectory should also start from zero velocity, right, and not some non-zero velocity, because if you give you non-zero velocity suddenly, then there will be a very jerky motion, right, that can harm the hardware. So what people did is just modify the trajectory such that at the very beginning, for some duration, there is a parabolic part, and at the very end there is a parabolic part, right? So what the let me draw it again. So it's like this, and it's ensured that it is smooth and continuous at both ends, right? So so let's mark few interesting points in these trajectories which will help us to derive the formulae. So let me pick a different. So this is not theta. So this is T0, this is TB, this is TF, the end time, this is TF minus TB, this is the halfway time TH, right? And corresponding to each, we will mark the joint angle values theta 0, here it will be theta B, here theta H, here it will be theta F minus B, and here theta F. Okay, so the criteria to find the unknown coefficients or unknown parameters of the trajectory is that the continuity should be maintained at these two joints, right? And one more term you should be familiar with is splines. Splines are basically joined. Generally spline is used when there is joined polynomials, right? So it will be like not one cubic but multiple cubics, or multiple cubics and linear, whatever. So you are piecing them together, so that is called as a spline, right? So now for simplicity, what people do is that they keep this initial and final time the same on both sides. So the parabolic part at the beginning and at the end, so we keep it of the same duration on both sides, right? And I am talking about here continuity, so position should be the same, of course, and the slope should be same, right? So here and here the slope should be same, and slope of this theta and t plot is the velocity. So velocity at this point TB, the velocity should match the velocity of the linear section, and the velocity of the linear section is the slope of the line, and similarly here too, right? So velocity should match at the junctions, and of course position should match. That need not be stated, it should match. So now if you see this plot, the average velocity in the parabolic part, right, that will be, so what, and also what we do is that we try to find out the acceleration in this part, right? So theta double dot, okay. So velocity at the end of parabolic part, first parabolic part is, let's say we have constant acceleration, so theta double dot times tb, right? This is the velocity. So, and we will write the velocity from the linear part also, and we will equate them. So from the linear part the velocity can be written as the slope of this line, right? The slope of this line, so slope is this tan theta. So from the linear part it is theta h minus theta b by th minus tb. Okay, and these two should be equal. So theta double dot tb is theta h minus theta b by th minus tb. So this is equating the velocity, right? And the second thing that we know is that theta tb, so using the equation of so simple equations of motions that we have studied in the school level, that is half a t square, right? So theta tv is the end joint angle at the end of the parabolic part, and since we have assumed constant acceleration, right, so it will be initial position plus half at square, so half theta double dot tv square, right? So this is equation 1 and this is equation 2, right? What we will do, we will put the value of theta b here. So put 2 in 1, so theta double dot tb into th minus tb theta h minus theta b, and theta b is theta 0 minus half theta double dot tb square, right? And this after simplification comes out to be theta double dot tb square minus theta double dot ttb plus theta f minus theta 0. Okay, so from this equation, so it's a choice, either you provide tb or you provide theta double dot. So generally we specify acceleration, because why specify acceleration? Because we know what are the capability of the motors, how much it can accelerate. So motors have some acceleration limits, right? So it's easier to specify what are the joint accelerations that we are looking for. And if we know this theta double dot, then it's a quadratic equation in tb, right? And tb can be expressed as t by 2 minus theta double dot, so basically just using the standard root of the quadratic equation formula, right? So this is the tb expression. And the discriminant should be greater than 0, right? So theta for real solutions, right? And of course we only need real solutions, should be greater than equal to 0, right? So this gives us a constraint on the acceleration, that acceleration should be at least greater than this, right? So for the spline we get this constraint, right? And the upper limit of theta double dot can be selected using the hardware, right? So motor limits. And if this lower limit itself comes more than the upper limit of the motor, then we would have to, change something. Maybe we have to increase time, we have to go slower. Okay, so this is the acceleration constraint. Okay, so that is all about the spline. And any question in the linear spline with parabolic blends? Okay, okay.
So no,
Yeah,
I don't
Karthik.
have doubt in this, sir, but I have a doubt in a different part. So can I ask now?
Yeah,
Or
you can ask.
okay, sir. In the previous session, we you gave an example of two coordinates. No, sir. One is fixed and one more is rotatable. Like
Mm-hmm.
while deriving the phi term
Mm-hmm.
acceleration.
Yeah, yeah.
There's a we have written like we have
Mm-hmm.
vrel term, and we also have omega cross RPA term, no, sir.
Yeah.
Um, that omega cross RPA is there, no? So that is due to the change in the direction of R vector, sir.
Yes.
Okay, okay. By changing the direction, it means the R vector can move towards left, right. It can rotate
Yeah.
more.
Basically, uh, so you can either say that the frame is the r vector is rotating with omega, or you can say that the frame itself is rotating with omega. So
Sir, if we think that way, then it omega cross RPA comes, no, sir. Like if we think the way you said.
okay, so uh, hmm right. So the first the expression which you asked about, it's due to the angular velocity of that position vector basically. So the the point p, right, the point p is on a body, the body is rotating with omega, so the contribution to the velocity of that omega is omega cross r. So that's simply this only, this quantity only. And
Like we can just
yeah, go on.
uh, we can just think that R vector is rotating around with that radius, whose length magnitude is remaining the same, but direction only the direction is changing. Can we say that way, sir?
Yes, you can say that. Yes, definitely. It's a r vector. The vector r points. It will be a position vector of a point p, right? And point p basically is rotating, and that's why the magnitude of r vector is not changing, but its direction is changing. Yes, you are right.
Okay, and because the translation is given by V rel
VREL.
vector.
Yes. So
Yeah.
when translation will happen, then the length of the r vector is also changing.
Only the length is changing, no, sir, at that time. Direction is not changing, right? At that time.
Yeah, like both can happen together also.
No,
That's why we have those two terms.
no. I didn't mean that way, sir. Like when we talk about the VREL term,
Hmm.
the R vector is changing in length. It is
Yeah,
not
yeah,
changing in
yeah,
direction, right?
yes.
Whereas in this omega cross RPA, the length is remaining the same.
Yes. They are
The
like
direction.
adding. You are adding two independent terms. They are not like affecting each other.
Okay.
Yes.
Yes, sir. That's clear, sir. Yeah. Thank you, sir. Thank you, sir.
Okay. So yeah. So today we solved a few questions on manipulator dynamics, and then moved on to trajectory planning, and we saw how to find out the uh, coefficients of the polynomials using which we are describing those trajectories. We saw how to use cubic polynomials, and also polynomials having multiple basically polynomials, which are like, an example is linear function with parabolic blend. So this is what we call as a spline. So, and it's up to the choice of the uh, person, that and also upon the requirement of the task, that which kind of trajectory is suited for that specific problem. So that's it from my side for today, and we will meet in the next discussion hour and continue on to sensors and actuators, and then on to the control part of the course. Okay, so uh, that's all for today, and we will meet next week.
Thank you, sir.
Okay.
Thank you, sir.